Hello guys, welcome back. In this video, I'm going to show you how to find the beam flexure reduction factor or beam bending capacity reduction factor. The general design strength equation for flexure is phi mn has to be greater or equal than mu. Mn is the nominal moment strength or beam bending capacity. Mu is the moment demand, is the moment that we find it due to the applied external load on our beam. So this is the variation of phi factor with epsilon t. Epsilon t is the steel strain in our beam. It is our horizontal axis and the vertical axis our phi. If epsilon t is equal or greater than 0.005, so the beam is tension controlled and our phi is 0.9. If epsilon t is equal or smaller than 0.002, the beam is compression controlled and our phi is 0.65. So this diagram is only for the stirrup tie or hoops. If it is a spiral tie, so that's a different diagram. If epsilon t is in between compression control and tension control, which is called transition zone, so we have to find that. So now, how do we find it? Let's take a look at it together. So this is the beam that we have. This is the D, and this is the DT from top to the middle of the bottom layer of steel rebars. So this is the A, or the first one is the strain distribution at tension control limit. And B, or the second one, is the strain distribution diagram at the compression control limit. So epsilon C is equal to 0.003 on both cases. It's a concrete strain at ultimate stress. C is distance from top to neutral axis on both cases. So as I mentioned earlier, if epsilon T is equal or smaller than 0.002, section is compression controlled. If epsilon T is equal or greater than 0.005, section is tension controlled. So we double check it in compression control, phi is 0.65, and tension control, phi is 0.9. So when analyzing a transition zone section, if you're located in between these two, if our epsilon T is located in between 0.002 and 0.005, so the value of phi varies linearly between 0.65 and 0.9 as a function of epsilon t. So we can find the phi using this equation. Phi is equal to 0.65 plus epsilon t minus 0.002 multiplied by 250 over 3. Note, I have a note here. If there is only one layer of steel, dt is equal to d. Let's take a look at an example together. So this is the example that we have. We have this beam with this hoop, and D is given, the BW is given, and the depth of the beam is given, or H. So we draw our strain diagram here. This is our epsilon S. It's for the steel, and this is our epsilon C for the concrete, 0.003 neutral axis. This here is D minus C, this here is C. So in order to find the epsilon S, so we use the triangle similarities between these two, top and bottom. So we get epsilon S is equal to epsilon C multiplied by D minus C over C. So our C is 6.95 inches. I already calculated this. We will have a different example on this, how to find C. So the goal for this video is to just show how to find phi. So these given, so you plug and check these values, we get epsilon is 0.00459. So since it's located in between compression and tension zone, so we use that equation. We use our equation 1, this equation, and find our phi. So we plug and check all those values and we get our phi 0.87. So our phi Mn is equal to 0.87 Mn. So this is the reference if you want to get more information about these kind of stuff. So reinforced concrete, mechanic and design, 6th edition, James K. White and James G. McGregor. Thank you guys for watching. I hope this video is helpful and help you guys on your homeworks. Thank you very much. Bye.